Welcome back to QHSE Talks. Usually when we talk about a medical diagnosis, there's this underlying expectation of absolute precision.
Right. It feels almost like engineering,
Exactly. I mean, you fall off a ladder, you break your arm, and the x-ray just shows that jagged white line right across the radius bone.
Yeah, the doctor just points at the screen and says, there it is. It's totally binary.
Right. Broken or not broken. It's clean, it's definitive. And as human beings, we find that incredibly comforting, right?
Oh, absolutely. We like things to be visible. We want them neatly categorized.
Yeah, because we want to know exactly what the threat is so we can mitigate it. But then, you step into the world of occupational safety.
Especially chemical hazard communication.
Yes. And historically, it was like someone just took a sledgehammer to that x-ray machine.
That is a great way to put it.
Yeah.
I mean, if you look back just a few decades, we were staring at a diagnostic landscape for chemicals that wasn't just murky. It was actively deceiving us.
It was a total mess, right?
It was the absolute definition of diagnostic muddy waters. I mean, before the global harmonization systems were unpacking and today's QHSE talks were put into place, a single chemical could be, diagnosed in completely contradictory ways.
Wait, depending on where you were.
Exactly.
Yeah.
Depending on where you were standing on the globe, you could literally have a barrel of solvent sitting on a dock. And the regulatory truth of how dangerous it was would change based on whose soil that dock was built on.
That's just wild to think about. And that kind of inconsistency is exactly why we're here today. We're talking directly to you, the listener, the dedicated safety practitioner.
Right, because your ultimate goal right now is preparing for the Associate Safety Professional exam, the ASP.
Yep. We know you're out there grinding, reading the textbooks late at night, trying to master these essential skills. And, you aren't just doing this to pass a multiple choice test.
No, not at all. You're doing it to perform your daily safety duties, right? Mm-hmm. To build resilient programs and protect lives on the factory floor.
Exactly. So here is our mission for this session of QHSE Talks. We are tearing into ASP Examination Blueprint Domain 2. That's the domain covering safety programs and concepts.
And specifically, we're targeting Topic 5, which is implement the globally harmonized system of classification and labeling of chemicals.
Or, as it's known to literally anyone who has spent more than 5 minutes in an industrial setting, the GHS.
Right, the GHS. And we truly cannot overstate the importance of this specific domain for you.
Oh, it's massive, isn't it?
It's a huge chunk. Domain 2 makes up a massive 25% of the entire ASP exam.
Wow. 1/4 of your final score.
Yeah, 1/4 depends on your mastery of these programs. But even more importantly, from a practical standpoint, GHS is the absolute bedrock of your facility safety architecture.
So let's frame the problem by going back in time a bit. Let's look at the historical chaos of chemical safety that actually forced the world to act.
Yeah. No,
because before GHS, there was this confusing, dangerous, completely fragmented patchwork of regulations.
Oh, it was a nightmare.
So let's imagine a scenario. Say you have a highly reactive chemical manufactured in a facility in Germany back in, 1991.
Okay, setting the scene.
Right. So over there, based on their specific national testing criteria, maybe they test for toxicity using a different exposure duration or something. They label it with a skull and crossbones.
Right. They just call it toxic.
Exactly. Then that same barrel gets loaded onto a cargo ship, crosses the Atlantic, and arrives in the United States.
And under the old OSHA hazard communication standards at that time.
Right, because the U.S. used a slightly different mathematical threshold for toxicity. That exact same barrel might just get a mild label that says harmful.
Which is a huge psychological difference for the worker handling it. And, consider flammability, which is arguably even more immediately catastrophic if you mishandle it in transit.
Oh, for sure. One spark and you're done.
Exactly. A chemical considered flammable in one country might not meet the exact temperature flashpoint criteria to be flammable in another.
So you have a dock worker in country A treating a pallet with extreme caution.
Right, utilizing grounding cables, using spark-proof forklifts.
But then a transport worker in country B receives that same pallet and is stacking it right next to a radiant heat source.
Or using standard sparking electrical equipment around it, simply because the label on his end doesn't trigger that same institutional alarm.
It's terrifying when you actually think about the sheer scale of global trade. I mean, we aren't talking about a few dozen barrels a year.
No, we're talking about millions of tons of hazardous materials crossing borders every single day.
Right. We're talking about systemic, dangerous mishandling in transportation, in the workplace, and even in consumer environments. It was just a complete structural failure to communicate risk.
And what's truly fascinating here, just from a purely scientific standpoint, is that the chemistry itself didn't change at all.
Right. The molecule is the molecule.
Exactly. The physical properties of the molecule, the vapor pressure, the boiling point, the way it interacts with human lung tissue, all of that remained exactly the same, whether it was Tokyo, London, or Chicago.
But the language we used to warn people about that molecule was effectively like a regulatory Tower of Babel.
A total Tower of Babel. Nobody was speaking the same language.
Which brings us to the core promise for today's QHSE talks. We want to assure you that by the end of this session, GHS won't just be a dry acronym that you memorize with index cards.
Right. It's going to be understood as the ultimate universal language of chemical safety.
Yeah. It's a system that translates physical, health, and environmental hazards into a globally recognized, mathematically standardized format.
It is the absolute foundation upon which all modern hazard communication is built. I mean, think about the other major topics in Domain 2 of your exam.
Yeah, like the hierarchy of controls.
Exactly.
Yeah.
You cannot apply the hierarchy of controls. You can't decide whether to substitute a chemical or install local exhaust ventilation or require respirators if you don't first accurately understand the intrinsic hazard of the material.
Right, and you cannot conduct a proper risk matrix if you don't have an objective measure of the severity of the threat.
And GHS provides that objective measure.
You know, I look at the GHS as the Rosetta Stone of occupational safety.
Oh, I like that analogy.
Yeah, because just as the actual Rosetta Stone allowed historians to finally decipher ancient hieroglyphics by giving them a parallel text, the GHS allows a worker in literally any country to instantly decipher the risks of a chemical.
Right, whether that 55-gallon drum was made in Taiwan, Germany, or the U.S.
Exactly. The visual language on that drum triggers the exact same conditioned safety response everywhere.
But to truly appreciate how this Rosetta Stone was carved, we really have to look at its origins. Because the global harmonization of chemical safety didn't just happen overnight.
Right, and somebody didn't just wake up and say, let's fix this.
No, it was born out of absolute necessity.
So take us back. Where did this massive, seemingly impossible global undertaking actually begin? Because getting the whole world to agree on something this complex sounds impossible.
Well, we have to travel back to 1992. The setting is the United Nations Conference on Environment and Development.
Okay, the Rio Earth Summit, right?
Exactly, the Rio Earth Summit. This was a monumental, historic gathering. You had world leaders, scientists, and policy experts all looking comprehensively at global sustainability and human health in the wake of rapid globalization.
So this is where the seed was planted.
Yes. It was in Rio that the genesis of a global initiative to tackle chemical hazard communication really took root.
What was the specific mandate that came out of Rio, though? Like, what did they actually say needed to happen?
The mandate was incredibly clear, but just dauntingly ambitious. They wanted to establish a single harmonized system to classify chemical hazards, standardize the labeling across all borders, and provide uniform safety data sheets.
That's a massive ask.
Huge. The UN basically looked at the chaotic web of international trade we just talked about and realized that individual regulation of hundreds of thousands of chemicals was completely impossible for any single nation to manage.
Right, because if the U.S. bans something or labels it strictly, but a trading partner doesn't, the supply chain just routes around it, right?
Exactly. Or workers just get caught in the crossfire of confusing documentation.
Right. So to execute this, they formed work groups under the UN umbrella.
Yeah, and these weren't just politicians. They pulled technical experts from all over the globe, regulatory agencies, massive chemical conglomerates, international labor organizations.
They needed buy-in from everyone.
They needed consensus from the people making the chemicals, the people regulating them, and the people actually breathing the air on the factory floors.
I can't even imagine the bureaucracy of those meetings. I mean, it wasn't an overnight thing, obviously. We're talking about aligning the legal frameworks of sovereign nations.
It took a full decade. 10 years of intense negotiation, scientific debate, and consensus building.
Wow. 10 years just to agree on the math.
Yeah, they had to agree on the exact mathematical cutoffs for things like flammability and toxicity. But the culmination of these efforts finally resulted in the official adoption of the system in December 2002.
And that's when they published the foundational document, right? The one with the distinct purple cover.
Yes, which is exactly why safety professionals affectionately refer to it as the Purple Book.
The Purple Book. It sounds almost mythical. But the Purple Book isn't a static, dead document, right? It's not like the UN wrote it in 2002, wiped their hands, and said, okay, we solved chemical safety forever.
No, not at all. Chemistry is a constantly evolving science. New toxicological data emerges all the time.
Right, and new testing methodologies get developed that can detect risks we couldn't even see 20 years ago.
Exactly. So to handle this reality, the UN established a permanent mechanism for ongoing maintenance. The United Nations Economic and Social Council, known as ECOSOC, created a specific subsidiary body to manage this.
And what is that body called for the exam takers out there?
It's the subcommittee of experts on the globally harmonized system of classification and labeling of chemicals.
That is a mouthful.
It really is. Or, if you prefer the acronym, UNSCEGHS.
Okay, I'll stick with that.
Their function is absolutely critical. They act as the permanent custodian of the GHS, they manage the harmonization process, they keep the system updated based on new data, and they issue revised editions of the Purple Book every couple of years.
Just to ensure the standard never falls behind the actual science.
Exactly.
Okay, let's bring this back to the reality of the safety professional working in the United States, because there's a timeline discrepancy here that is pretty fascinating.
Oh, the adoption timeline, yeah.
Right. The UN adopts this groundbreaking system in 2002. Some early adopters internationally jump on board relatively quickly, right?
Yeah, countries like New Zealand, Japan, Korea, and Taiwan, they integrated it into their national frameworks pretty fast.
But the United States Occupational Safety and Health Administration, OSHA, they didn't fully integrate this until they issued a major revision to the Hazard Communication Standard, what we now call HAZCOM 2012.
Yes, 29 CFR 1910.1200. The 2012 revision is what finally aligned the U.S. regulatory standard with the global GHS framework.
Wait, hold on. I have to play devil's advocate here for a second.
Go for it.
If this massive global consensus started in 1992 and the Purple Book was literally published and ready to go in 2002, why did it take a full decade for a country with the resources of the U.S. to transition?
That is a phenomenal question.
Was that delay due to, massive lobbying and resistance from chemical manufacturers, or was it just the logistical nightmare of physically relabeling millions of products?
It's really a combination of complex factors, and understanding the answer gives you a lot of insight into how safety regulations actually work in the real world.
Okay, so what was the first hurdle?
First, consider the regulatory mechanism in the United States.
Yeah.
Under the OSH Act of 1970, changing an OSHA standard is a monumental administrative and legal process.
You can't just flip a switch and say new rules tomorrow.
Exactly. It requires extensive economic impact analyses, small business advocacy review panels, lengthy public comment periods, and stakeholder hearings.
Wow, that's a lot of red tape.
It is intentionally slow and deliberate to ensure all economic and safety voices are heard, and that the rule can actually withstand legal challenges.
So regulatory friction. Necessary friction maybe, but still a really slow-moving machine.
Precisely. Secondly, you cannot understate the logistical reality for the manufacturers. It was daunting.
Right, because OSHA was asking an entire industry to completely overhaul their hazard determination processes from the ground up.
Yes, they had to reclassify every single mixture they produced based on new, stringent mathematical criteria. They had to graphically redesign every label on every bottle, drum, and tank.
And rewrite all the paperwork, too.
Yeah, they had to completely rewrite every single material safety data sheet into a new, rigid 16-section format. That requires massive capital investment, legal review, and time.
But despite that massive hurdle, it did get done. But why was the UN ultimately successful in pushing this through globally when so many other international agreements just fall apart?
Well, because the UN already had a massive, highly successful foothold in one specific sector of chemical handling.
Which sector?
The transport sector. For decades, the transport sector's maritime, aviation, rail, and highway already had robust schemes in place for moving dangerous goods.
Oh, like those diamond-shaped DOT placards on the back of tanker trucks.
Exactly. The red one with a flame or the white one with a skull, those were largely harmonized globally well before GHS.
Ah, because you had to have them to prevent catastrophic shipping disasters, right? And to tell highway responders what was inside a burning truck.
Right. So the roads and the oceans were already somewhat harmonized.
So where was the failure? Where did the system break down?
The massive gap existed at the end of the journey. A chemical might be strictly regulated and universally understood while it was inside a shipping container on a train.
But the moment that container arrived at a destination.
Exactly. The moment the barrel was taken off the train and opened on a factory floor, the harmonized communication simply stopped. The workplace and consumer safety regulations were a chaotic mess.
I see.
GHS bridged that gap. It took the universal language of the transport sector and forced the existing disparate systems for workplace and consumer safety to converge with it.
That paints a really clear picture. It's like we had perfectly standardized traffic lights and road signs for the interstate highways, but the moment you pulled off the highway and into the factory parking lot, it was a completely unregulated free-for-all.
Right, where everyone drove by their own rules.
And GHS finally paved the roads inside the facility and put up standardized stop signs.
Exactly. And now that we understand that historical imperative and how the system was born, we need to transition into the technical application.
Right, because for the ASP exam and for your daily job, you need to know exactly what falls under the jurisdiction of this massive system.
Let's define the boundaries.
Yeah. What exactly does GHS apply to? Like if I'm walking through a manufacturing plant, what materials are governed by this purple book?
According to the GHS framework, the system applies universally to pure chemical substances, their dilute solutions, and chemical mixtures.
Okay, so pretty much everything chemical.
Yeah. If you have a substance that poses an intrinsic physical hazard, a health hazard to humans, or an environmental hazard, it falls directly under the purview of GHS classification and hazard communication.
Okay, pure substances like raw benzene, dilute solutions like an industrial cleaner, and complex mixtures like a specialized solvent. That makes intuitive sense.
It does.
But here's the tricky part that I know trips up a lot of people studying for the exam. There is a massive, highly specific exemption to this rule.
Yes, there is.
GHS explicitly defines what is exempt, and the magic word here is articles.
Yes, articles. As defined by OSHA in 29 CFR 1910.12000 and by similar competent authorities globally, they are completely outside the scope of GHS.
So if something is deemed an article, no GHS label, and no safety data sheet.
Correct.
I think we really need to dive deep into this article exemption because the line between a hazardous mixture and an exempt article can seem pretty blurry on a factory floor.
You definitely can.
Let's explore a scenario. Let's say my facility manufactures those hard plastic chairs you see in waiting rooms.
Okay, classic example.
Those chairs are made of complex chemical polymers, colorants, and plasticizers. During the manufacturing process, when those raw chemicals are being heated and mixed, they are absolutely hazardous, right?
Oh, without a doubt. They emit fumes, they can be toxic, they were subject to strict GHS regulations.
But once that plastic is molded into a solid chair and cools down, it suddenly becomes an article.
That is exactly how the exemption works. The OSHA definition of an article hinges on a few very specific criteria that you must memorize for the exam.
Okay, lay them out for us.
First, it has to be a manufactured item, other than a fluid or particle, which is formed to a specific shape or design during the manufacturing process.
Okay, check. A chair is shaped like a chair. What's the second?
Second, its end-use function has to be dependent, in whole or in part, upon that specific shape or design. The chair works because it is shaped like a chair.
Right. And the third criteria, because, a lead pipe is shaped like a pipe, but lead is dangerous.
The third, and most crucial criteria, is the exposure potential. Under normal expected conditions of use, the item cannot release more than very small quantities, what OSHA calls minute or trace amounts of a hazardous chemical.
And it must not pose a physical hazard or health risk to employees.
Exactly.
Okay, so let's push the boundaries of that definition. What about a steel beam?
Okay, a solid steel beam.
Right. A solid steel beam is an article. It's shaped for a purpose. It doesn't emit gas while it's holding up a roof.
Right.
But what if my workers are taking grinders to that steel beam or welding it, which releases highly toxic hexavalent chromium fumes? Does the article exemption still apply if the end user is altering it?
That is a brilliant nuance, and it's exactly the kind of critical thinking required of a safety professional. In the case of the steel beam being welded or ground down as part of its normal expected use in a fabrication shop, the manufacturer does have to provide hazard communication.
Oh, they do?
Yes. They have to provide an SDS and labeling because they know that the expected downstream use will release hazardous fumes.
Ah, I see.
However, if the steel beam is just being bolted into place and not altered in a way that releases chemicals, it functions as an exempt article for the end user.
That makes perfect sense. The exemption is intrinsically tied to the potential for human exposure during normal use.
Exactly. If a manufactured item's shape is what makes it useful, and it traps the hazardous chemicals inside safely.
Like a plastic chair, a steel hammer, or the plastic housing of a ballpoint pen.
Right. Then it escapes GHS regulation for the consumer or the office worker. If you are an office safety manager, you don't need a massive yellow binder full of safety data sheets for the pens and staplers on people's desks.
Thank goodness for that. But if you are the safety manager at the facility manufacturing those pens,
then you absolutely need comprehensive GHS labels and SDSs for the bulk liquid ink in the vats and the raw plastic pellets in the hoppers.
Yeah.
Because there, the chemical hazard is active and exposure is possible.
Okay, let's expand on who exactly the system is built for. We've talked about the factory floor. But GHS isn't just for the industrial hygienist in the hazmat suit, is it?
Not at all. The target audiences are much broader. The UN designed GHS to be adaptable.
So it's not a one-size-fits-all.
No. Competent authorities,
Right.
which means the legal regulatory bodies in a given country, like OSHA in the US or Health Canada, they decide how to apply the GHS framework based on the needs of 3 distinct target audiences:
Which are?
the workplace, the transport sector, and consumers.
This brings up a concept I found really fascinating in the source material. The texts describe GHS not as a rigid monolith, but as a building block system.
Yes, the building block approach.
What does that mean in practical terms? I mean, if the goal is global harmonization, why allow countries to pick and choose blocks? Doesn't that invite the very chaos we were trying to escape?
It's a very perceptive question. What's fascinating here is how the UN structured the political and practical adoption process.
Because they had to get people to actually agree to it.
Right. They knew that if they forced a rigid all-or-nothing system on every country and every industry simultaneously, the entire initiative would just collapse under its own weight.
So they made it modular.
Exactly. GHS is a modular building block approach. The competent authorities can choose which specific harmonized classification and communication elements to apply based on the specific audience they are regulating.
Give me a real-world example of how these building blocks are applied differently. Like, how does an OSHA workplace block differ from a consumer product block?
Well, consider how a consumer at a grocery store perceives risk versus a highly trained chemist in a lab. The GHS framework acknowledges this psychological difference.
Okay, how so?
A competent authority might require incredibly strict, highly detailed hazard statements and multiple pictograms on a massive 55-gallon drum of a corrosive industrial chemical destined for a manufacturing plant.
Right, because the workers there need the deep science.
Exactly. But for a highly diluted consumer-grade version of a similar chemical, say a household drain cleaner under your sink, the regulatory authority might utilize a different building block.
They might base the consumer product label on the likelihood of injury, given the small volume, rather than just the intrinsic hazard of the raw chemical.
Precisely.
That makes total sense. A consumer label needs to be immediate, direct, and actionable without requiring a degree in chemistry.
Keep out of reach of children. Wear rubber gloves. Call poison control if swallowed. Very simple.
Right. While the industrial label needs to tell the safety professional exactly what target organ systems will fail if the vapor concentration exceeds a specific parts per million threshold.
Exactly. It's about communicating the right level of data to the right audience. And this is the vital, non-negotiable rule of GHS.
What's the rule?
While the final labels might look slightly different between a consumer bottle and an industrial drum, the underlying science must be identical.
Ah, so the math doesn't change.
Right. Using an identical set of mathematical categories at a worldwide level within each sector is highly encouraged. A chemical defined as a Category 1 flammable liquid must be defined by the exact same flashpoint criteria everywhere.
So the math is harmonized, even if the building block of communication is tailored to the audience.
Yes.
Okay, so knowing what is covered, pure substances and mixtures, and who it is for, we must now look at how these hazards are practically communicated to the people handling the materials.
The physical labels.
Yes. The very first line of defense, long before anyone opens a binder, is the visual label.
Because if you're walking through a busy, loud warehouse and you see a pallet of containers,
You don't have time to pull out a manual. That label is everything. It is the front line of hazard communication.
and that transition brings us to the strict architecture of the label itself.
Under the old pre-GHS OSHA hazard communication standard, labels were what they called performance-oriented, which basically meant the government said, hey, manufacturer, just make sure you tell people this stuff is dangerous somehow. Do your best.
Yeah, do your best. It was a wildly subjective, almost chaotic system.
Because it was performance-oriented, you could convey the hazard almost any way you wanted, right?
As long as you could argue it met the performance metric. You could use different colors, different phrasing, different font sizes, different emphasis.
One company might use a big red stop sign. Another might just use bold black text.
It led to incredible confusion, especially for workers moving between different facilities or handling products from multiple vendors.
And GHS ended that subjectivity completely.
Completely. GHS imposes strict, rigid, unyielding requirements for a label. It surgically removes the ambiguity.
I compare the old labeling system to a Wild West of warning signs, where every town sheriff drew their own map of the dangers.
And GHS labels are like modern traffic lights.
Yes. Standardized, universally understood, and structurally engineered to trigger an immediate condition safety response in the human brain.
Red means stop, green means go. GHS has its own absolute rules.
So for the listener taking notes for the ASP, what are the mandatory elements? If I'm looking at a fully compliant GHS label on a drum, what 6 things must be physically present?
Lock these 6 elements in your memory because they are foundational. Element number 1, the product identifier.
The name of the chemical.
Yes.
Yeah.
This is the exact chemical name or code number that links the label directly to the safety data sheet. This is critical because it prevents you from reading the wrong safety information for the chemical sitting in front of you.
Element 2, supplier identification.
Right. This must include the name, address, and an emergency telephone number of the manufacturer, the importer, or other responsible party.
Because if a drum ruptures at 2 a.m. on a loading dock, the emergency responders need to know exactly who to call to get immediate expert mitigation advice.
Exactly. Then we have element 3, which is a massive one, the signal word.
The signal word is a massive psychological trigger.
Oh, absolutely. Under GHS, there are only 2 signal words allowed, danger and warning. It's just 2. Danger is reserved for the more severe hazards, typically categories 1 and 2 of a specific hazard class. Warning is used for less severe hazards.
It's entirely binary.
It immediately tells the worker the severity of the threat before they even read the fine print.
It's elegant in its simplicity. Danger means this substance could kill you, blind you, or cause catastrophic facility damage very quickly.
And warning means this substance will hurt you, it will cause a fire, or it will damage the environment, so you need to pay strict attention.
Essentially setting the baseline anxiety level for handling the material.
Exactly. Then we move to element 4, hazard statements.
And these are not subjective warnings, though.
No, they are plain language, standardized alphanumeric codes that describe the exact intrinsic hazard of the chemical.
Give us a concrete example of a hazard statement. How does it differ from the old way of doing things?
Under the old system, a manufacturer might write, use caution, contents may ignite if they get too hot.
Which is pretty vague.
Very vague. Under GHS, a classic example is the code H222. That specific alphanumeric code translates universally to the exact mandated phrase, extremely flammable aerosol.
Yeah.
Or take a health hazard code like H304. That translates exactly to may be fatal if swallowed and enters airways.
So a manufacturer cannot get creative. They cannot soft pedal the danger with marketing spin.
Absolutely not. They must use the exact GHS phrase assigned to that specific mathematical hazard category.
It's brilliant because it removes the corporate PR department from the safety equation.
Completely.
Okay, element 5 is the pictograms, which we will dedicate an entire exploration to in a minute because they are so critical to the visual language. What is the final 6th element?
Element 6. Precautionary statements.
So while the hazard statement tells you what the danger is,
A precautionary statement tells you how to protect yourself. These are the recommended measures to minimize or prevent adverse effects.
and they're divided into categories.
Yeah, logically divided into 4 areas.
Yeah.
Prevention, response, storage, and disposal.
So a prevention statement might be wear protective gloves and eye protection.
Right, and a storage statement might be store in a well-ventilated place away from direct sunlight.
So to recap the mandatory 6 for the exam, product ID, supplier info, signal word, hazard statement, pictogram, precautionary statement.
You got it.
Now, that works perfectly for a single drum of chemicals, but what happens in the real world when we have a complex packaging situation?
Oh, this is where it gets tricky.
Let's explore the market kit example provided in the blueprint sources. Let's say my facility orders a comprehensive water testing chemistry kit for our environmental lab.
Okay.
You have a large outer cardboard box, and inside that box are 10 small glass bottles, each containing a completely different chemical reagent.
A very common scenario.
How does the GHS framework handle that logistical nightmare? Do I need 10 different labels on the outside of the box?
This raises an incredibly important question about practical logistics and visual clarity. According to the strict GHS guidance, if you have an outer packaging box with multiple inner chemical bottles, the outer box must display the kit identifier, the supplier info, and the general storage statements.
Okay, that makes sense.
But crucially, when it comes to the signal word, it must display the signal word that is the most stringent assigned to any single component inside that box.
Oh, wow. So if there are 9 bottles of mild skin irritants that only mathematically trigger a warning signal word, but there is one tiny 10 milliliter bottle of a severe Category 1 corrosive that triggers danger.
The outside of the entire large box must scream danger.
That is intense. The most severe hazard dictates the outer warning.
Exactly. Furthermore, the outer box must also display the pictograms for each single hazardous substance contained inside, but it must do so without duplicating any pictograms.
So if 5 bottles are flammable, you only put 1 flame on the outer box.
Right. You don't want 5 flames cluttering the box. And finally, the outer label must prominently state, "Read full label enclosed."
This entire protocol ensures that anyone handling the outer box, a receiving clerk, a forklift driver, treats it with the absolute respect demanded by this single most dangerous item inside.
Without overwhelming them with redundant symbols.
Speaking of redundant symbols, there is a really important rule regarding transport labels on these outer boxes.
Yes, the intersection with transport rule.
Right. If I have a large cardboard box on a shipping pallet and it already has the DOT transport diamond on it, say, that familiar red diamond with the flame for a flammable liquid, do I also need to stick the GHS red-bordered flammable pictogram right next to it?
No, and this is a highly testable concept for the ASP because it deals with intersecting regulations. The rule is specifically designed to prevent redundancy and visual clutter.
So I don't need both.
Correct. If a UN model regulations transport pictogram like that DOT diamond appears on the outer label for a specific hazard, a GHS pictogram for that same exact hazard should not appear.
Because you don't want a label covered in 3 different, slightly varied fire symbols.
It creates visual noise and confusion. The transport label takes precedence for the external packaging during shipping.
The entire labeling system relies so heavily on those visual symbols to bypass language barriers entirely.
Has to.
Because you can have a worker who doesn't speak a word of English or who has low literacy, but human evolutionary psychology guarantees they understand that a skull and crossbones means death, or a flame means fire.
Exactly.
Let's dive deep into the specific standard pictograms and the mathematical hazard classifications they represent, because this is where the chemistry really meets the communication.
Let's first precisely define what a pictogram actually is under the GHS standard, because it's not just a random drawing.
Right, it's highly regulated.
It is a highly regulated graphical composition that includes a symbol, a border, and a background pattern intended to convey specific information instantly.
So what does that look like specifically?
For GHS, this means a solid black hazard symbol, set on a stark white background, framed by a thick red diamond-shaped border. The contrast is designed for high visibility in low-light industrial environments.
There are 9 standard GHS pictograms.
Yes, 9. And they broadly represent 3 hazard groups: physical hazards, health hazards, and environmental hazards.
Let's walk through some specific classifications detailed in the blueprint text, because this is where the safety professional has to really know their underlying science.
Let's start with a very common physical hazard that causes catastrophic industrial accidents: flammable liquids.
Okay, flammable liquids. They are divided into rigid categories based entirely on their flash point and their initial boiling point, correct?
Yes. The flash point is the lowest temperature at which a liquid gives off enough vapor to ignite in air. Category 1 is the absolute most dangerous. These are extremely flammable liquids with very low flash points and low boiling points.
So they ignite very easily.
Category 2 is highly flammable, and Category 3 is flammable. All 3 of these categories require the flame pictogram.
And the signal words.
Categories 1 and 2 require the signal word danger, while Category 3 requires warning.
But here is a crucial nuance for the ASP exam and something I want to challenge. What about Category 4 flammable liquids?
Category 4 is scientifically classified as a combustible liquid. These have a higher flash point, typically between 60 degrees and 93 degrees Celsius.
And what's the exception here?
This is the exception you must memorize. Category 4 requires no pictogram whatsoever.
Wait, really? No pictogram?
None. It only requires the signal word warning and the hazard statement, combustible liquid, which is code H227.
Wait, if the whole point of GHS is to universally communicate hazards, why are we letting manufacturers completely drop the flame pictogram for a Category 4 liquid?
I know it sounds counterintuitive.
I mean, a combustible liquid will still burn and cause a massive factory fire if it gets hot enough. Doesn't removing the pictogram just invite a worker to treat it like it's completely safe? How does that not cause accidents?
It's a very valid concern, and it gets to the heart of human factors engineering. It is entirely about preventing warning fatigue.
Warning fatigue?
Yes. If we mandate a bright red flame diamond on a heavy oil that requires substantial sustained intentional heating to ever catch fire,
right,
we put that exact same red flame on an aggressive solvent like acetone that will ignite at room temperature from a microscopic static spark off a worker's sweater. We dilute the psychological impact of the symbol.
If everything is presented as an immediate life-threatening emergency, then the human brain adapts and decides that nothing is an emergency.
Precisely. The GHS criteria are scientifically harmonized to reserve the extreme visual alarms for the threats that require immediate conditioned responses.
So a Category 4 liquid requires safe storage, absolutely, but it doesn't require the explosive-proof electrical protocols of a Category 1 liquid.
Exactly. The lack of a pictogram correctly communicates that lower relative risk.
That makes a lot of sense from a behavioral psychology standpoint. Okay, let's look at another fascinating and frankly terrifying category mentioned in the sources, desensitized explosives.
Oh, this is a highly unique category. These are solid or liquid explosive substances that are just too dangerous to transport or handle in their pure state.
So what do they do with them?
They are intentionally wetted with water or alcohols or diluted with other inert substances to suppress their explosive properties. They are essentially tamed sleeping explosives.
But the danger is that if that desensitizing agent, the water or the alcohol, evaporates or is reduced through a leak or poor storage, the beast wakes up.
Yes, the explosive potential returns. The risk of a catastrophic explosion increases significantly if the desensitizing agent is reduced.
So how does GHS handle that?
Under GHS, categories 1 and 2 of desensitized explosives use the signal word danger and the very specific hazard statement. Fire, blast projection hazard, increased risk of explosion if desensitizing agent is reduced.
And categories 3 and 4?
They use the signal word warning. But here's the kicker. All 4 categories require the flame pictogram, not the exploding bomb.
Wait, really? Not the bomb?
No, because the primary risk in their desensitized state is intense fire.
Fascinating. Then we have self-reactive substances. The name alone sounds unstable. What makes a chemical self-reactive?
These are thermally unstable liquid or solid substances liable to undergo a strongly exothermic, meaning heat-releasing decomposition, even without the participation of oxygen.
So they don't even need air to burn or explode?
Nope. They just need a trigger, like heat, friction, or shock. GHS categorizes them on a spectrum from type A to type G based on their laboratory kinetics.
Walk us through the extremes of that spectrum.
Type A is the absolute most severe. It can detonate or deflagrate rapidly as it is currently packaged. It requires the exploding bomb pictogram and the signal word danger.
And as you move down?
As you move down the types, the severity lessens. Types B, C, D, E, and F require either the exploding bomb or the flame pictogram, and danger or warning depending on the specific reaction kinetics.
But again, look at the cutoff principle.
Right. Type G self-reactive substances require no pictogram, no signal word, and no hazard statement.
Because the scientific criteria determine that the risk of a runaway thermal reaction has dropped below the threshold of needing a standardized warning.
Exactly.
Okay, let's shift gears from physical hazards, the fires and explosions, to health hazards. These are often the insidious threats, right?
Well, ones that might not blow up the facility today, but will destroy a worker's health over years of chronic exposure.
Exactly. Let's start with skin sensitization.
A skin sensitizer is a substance that will lead to an allergic response following skin contact. It might not burn you like an acid, but your immune system reacts violently.
How are these categorized?
GHS categorizes these as Category 1, with subcategories 1A and 1B based on the frequency of occurrence in human populations and the intensity of the allergic reaction.
And the labeling.
They use the exclamation mark pictogram, the signal word warning, and the hazard statement H317 may cause an allergic skin reaction.
How about STOT? Specific target organ toxicity. This seems like a massive area for industrial hygienists.
It is a critical one. COT looks at non-lethal but severe, specific, and often irreversible damage to a specific organ system like the liver, the kidneys, or the central nervous system.
And it differentiates between single and repeated exposures.
Yes, it differentiates between damage from a single massive exposure versus repeated chronic exposures over time. For COT single exposure Category 1, the system demands the specific health hazard pictogram.
Which is the silhouette of a person with a starburst radiating from the chest.
Right, exactly. And it uses the signal word, danger.
And the hazard statement for CO Category 1 is intense, isn't it? It's not vague.
It is highly specific. Mistake causes damage to organs, and then it requires the manufacturer to explicitly list all the specific organs affected if that data is known.
And the route of exposure.
Yes, it must state the route of exposure like inhalation, oral, or dermal if it is conclusively proven that no other routes cause the hazard.
So it's not just a generic bad for your health, it's danger. Causes damage to the liver and kidneys via inhalation.
Exactly.
That is highly actionable information. Because if I know the road is inhalation, I know I need to focus my engineering controls on ventilation and respirators, rather than just chemical gloves.
Precisely. You use the label to build the control.
Finally, let's touch on the aspiration hazard.
Aspiration toxicity includes severe acute effects such as chemical pneumonia, varying degrees of pulmonary injury, or death following aspiration.
Which is when liquid gets into the lungs, right?
Yes. Aspiration is the entry of a liquid or solid directly through the oral or nasal cavity, slipping past the epiglottis and settling into the trachea and lower respiratory system.
Scary stuff.
It's often related to the surface tension and viscosity of the liquid. Category 1 uses the health hazard pictogram, the signal word danger, and the statement H304, may be fatal if swallowed and enters airways.
If we pull back and connect all of this deep chemistry to the broader objective of the ASP exam, you need to understand that the criteria for these categories are mathematically and scientifically harmonized.
Yes, they are.
Category 1 always means the most severe threat in any hazard class. This systematic categorization is the absolute bedrock for a safety professional. You can't mitigate a risk if you can't accurately quantify the severity of the hazard.
That is exactly right. The label and the pictograms are vital. They act as the emergency alarm and the quick reference guide on the shop floor, but they have a severe limitation: physical space. A label on a 1-gallon jug can only hold so much text.
Which means when a safety professional or an industrial hygienist or an emergency medical responder needs the full story,
When they need the deep chemistry, the exact permissible exposure limits, the long-term ecological impact.
right, the engineering controls, they can't just look at the bottle, they have to turn to the foundational document.
They turn to the safety data sheet.
And that brings us to the architecture of the SDS, the 16-section blueprint.
This was a massive paradigm shift in the industry. Anyone who has been in safety for a while remembers the old days of the MSDS, the Material Safety Data Sheet.
Oh man, it was, frankly, a nightmare.
It was wildly inconsistent. Under the old NSDS systems, the manufacturer was legally required to provide the safety information, but they could arrange it however they saw fit.
Some documents were 3 pages long, some were 15 pages.
Some put emergency first aid on page 1 right at the top. Others buried it in a dense paragraph on page 10 under a different heading.
I always compare the old MSDS system to a completely disorganized library where every single author arranged their book chapters differently.
Great analogy.
Imagine trying to find the index of a book, but in some books it's in the middle, in others it's at the front, and in some it's just missing entirely.
Exactly. And the GHS SDS is like a highly structured encyclopedia. GHS mandated a strict, rigid 16-section architecture.
And for the ASP exam, you absolutely must know these 16 sections, and you must understand the logic of their exact mandatory order.
But we aren't just going to recite numbers 1 through 16 like a textbook.
Right, that's boring.
To really understand the genius of the GHS SDS, we need to group these sections logically by how they are used in the real world. Let's imagine you are holding an SDS in your hand right now. We can break it down into the 3 functional clusters.
I love this approach. Let's start with the first cluster, I call this the emergency response cluster. This covers sections 1, 2, 4, 5, and 6.
These are the sections you need when adrenaline is pumping, an alarm is ringing, and seconds matter.
Exactly. Section 1 is identification. What is this chemical and who made it? It includes the emergency phone number.
Section 2 is hazard identification. This is where you find the exact GHS classification, the signal word, the pictograms, and the hazard statements. It answers the immediate question. How dangerous is the situation I'm looking at?
Then we skip to Section 4, first aid measures. This is arguably the most critical section in an emergency.
It provides necessary first aid instructions categorized by relevant routes of exposure, inhalation, skin and eye contact, and ingestion.
And crucially, it must be written in layman's terms so a frantic coworker can understand it, not just a doctor. It lists the most important acute and delayed symptoms.
Then we have the facility emergency sections. Section 5 is firefighting measures. If the chemical is burning, you need to know the suitable extinguishing media.
Should you use water, foam, or dry chemical? Using water on a reactive metal fire will cause an explosion. Section 5 prevents that.
Section 6 is accidental release measures. If a 55-gallon drum tips over, this section tells you the immediate personal precautions, the emergency procedures, and the safe containment and cleanup methods.
So that's the emergency response cluster. You have a spill, a fire, or an exposure, you hit sections 1, 2, 4, 5, and 6. Now let's look at the second group. I call this the engineering and handling cluster.
This is for the safety professional who is calmly setting up a new production line and needs to design the physical safety systems. This includes sections 7, 8, 9, and 10.
Right. Section 7 is handling and storage. It details precautions for safe handling, conditions for safe storage, and explicitly lists incompatible chemicals to avoid.
You don't want to store a strong oxidizer right next to a flammable fuel. Section 7 tells you that.
And then we hit Section 8. This section is the absolute bread and butter for the safety professional and the industrial hygienist.
Absolutely. Section 8 is exposure controls and personal protection. This is where you find the hard regulatory control parameters.
It lists the OSHA permissible exposure limits, the PLs, and the ACGIH threshold limit values, the TLVs.
It details the appropriate engineering controls needed, like local exhaust ventilation specifications. And it dictates the specific individual protection measures, such as the exact type of respirator cartridge or the specific polymer of chemical glove required.
If you need PPC info, your eyes just jump straight to Section 8 every single time. Then you need the physical data to back up your engineering controls, which is Section 9, physical and chemical properties.
Appearance, odor, pH, melting point, flash point, flammability limits, vapor pressure.
Note a small quirk for the exam. The order of the individual properties within this section is not strictly mandatory, but the section itself must be Section 9.
And tying off the engineering cluster is Section 10, stability and reactivity. Is the chemical stable under normal ambient conditions? What specific conditions should be avoided, like static discharge, shock, or vibrations?
What incompatible materials will it violently react with to produce toxic gas?
Exactly.
Finally, we have the third group, the deep science and regulatory cluster. This includes the remaining sections, 3, 11, 12, 13, 14, 15, and 16.
These are for in-depth risk assessments, environmental planning, and legal compliance.
Section 3 is composition and information on ingredients. This lists the chemical identity, CAS numbers, and concentration levels of all hazardous ingredients.
But there is a key rule here. Competent authority rules for confidential business information or trade secrets take priority here.
So a manufacturer can withhold the exact chemical formula to protect their intellectual property.
Yes, but they must still disclose the hazard category of the mixture.
Wait, if the whole point is universal hazard communication, why are we letting manufacturers hide behind trade secrets? Doesn't that defeat the purpose if I don't know exactly what my workers are handling?
It's a delicate balance between safety and capitalism. The compromise GHS strikes is that you can hide the exact recipe, say 12% of chemical X and 8% of chemical Y, but you cannot hide the result of that recipe.
I see.
If the mixture is a Category 1 flammable, you have to disclose that hazard and the required controls, even if you keep the exact proprietary formula a secret. The safety data is communicated, even if the intellectual property is shielded.
Okay, that makes sense. Moving on to Section 11, toxicological information. This is the deep medical data.
It provides toxicological data on effects such as acute toxicity, skin corrosion, serious eye damage, respiratory sensitization, germ cell mutagenicity, carcinogenicity, and reproductive toxicity.
It lists the numerical measures of toxicity, like the lethal dose for 50% of a test animal population.
Let's pause here and analyze the structural logic of the entire document. Why is First Aid Section 4 way up near the front, while Toxicological Information Section 11 is buried in the back half?
It's a textbook example of safety through design applied directly to document formatting.
Exactly.
In an emergency, a worker or a paramedic needs to know what to do immediately if a chemical is splashed in someone's eyes. They need Section 4 instantly.
They do not have the time nor the need to read about the LD50 rat studies or the long-term germ cell mutagenicity risks in that critical adrenaline-fueled moment.
Section 11 is for the industrial hygienist sitting at a desk doing a long-term risk assessment, not the responder dealing with a spill. The document is engineered ergonomically for the user's needs in real time.
That is exactly the insight the exam is testing for. You aren't just memorizing a list, you are understanding the intent of the system.
Rounding out the final sections, Section 12 is ecological information. Ecotoxicity, persistence, and degradability, bioaccumulative potential.
If this chemical gets into the groundwater, will it build up in the local fish population?
Section 13 is disposal considerations. How do you safely handle the waste residues?
Section 14 is transport information. The UN number, UN proper shipping name, transport hazard classes, packing group. This ties directly back to those DOT placards we discussed earlier.
Section 15 is regulatory information. Any safety, health, and environmental regulations specific to the product that aren't indicated anywhere else.
And finally, Section 16, other information. This includes information on the preparation and revision dates of the SDS itself, ensuring you are reading the most current version.
And it is important to note that the SDS is not a fixed-length document, right?
It's not a standard two-page form like a tax return. As the UN guidance explicitly states, the length of the SDS should be commensurate with the hazard of the material and the information available.
A simple salt solution might have a basic 3-page SDS. A highly complex, highly toxic reactive polymer mixture might have 8 dense 25-page SDS. We have covered an immense amount of technical knowledge today. We've covered the history, the boundaries, the visual labels, the intricate chemistry of the hazard categories, and the rigid 16-section architecture of the SDS.
But knowledge is only truly valuable if it is applied.
We must now synthesize this and apply it directly to the ASP exam and the safety professional's daily duty.
This is where we connect the theory to the daily reality of your career on the floor.
First, let's define the role itself. What does a safety professional actually do?
According to the blueprint, a safety professional applies expertise from safety science to create procedures that predict and control hazards.
To even sit for the ASP exam, you must meet strict academic and professional experience requirements. You must be actively performing at least 50% professional-level safety duties.
Those duties include worksite assessments, hazard recognition, evaluating risk control measures, and crucially for today's topic, managing hazardous materials. As we mentioned, the ASP is a full certification proving competency in fundamental safety concepts.
So how do we practically connect the GHS standard back to those daily workplace duties you have to prove competency in?
GHS is the operational baseline. You cannot build a compliance program without it. Employers must maintain a comprehensive, updated list of all hazardous chemicals used in the workplace.
They must ensure proper GHS labeling on every single container, including secondary containers, when a worker transfers a chemical from a 55-gallon drum to a spray bottle.
They must have the 16-section SDS readily available and accessible to employees on all shifts. And, perhaps most importantly, they must train employees comprehensively on this entire system.
We mentioned earlier that OSHA transitioned to HAZCOM 2012 to mandate the switch to these standard formats. But OSHA doesn't instantly adopt every single UN update to the Purple Book, right?
Correct. The UN updates the Purple Book every 2 years to reflect new science and new chemical discoveries. OSHA's rulemaking process is much slower.
So while OSHA HAZCOM 2012 is perfectly aligned with the core GHS formats, it might lag slightly behind the absolute latest UN revision in terms of highly granular chemical classifications.
But the architecture, the 16 sections, the 9 pictograms, the signal words, that is now the permanent regulatory law of the land.
For the listener preparing for the exam, what is the biggest trap here? Is the trap just failing to memorize the specific order of the 16 sections, or is it something deeper?
The memorization of the list is the easy part. You can drill that with flashcards. The dangerous trap is failing to synthesize the information.
So it's failing to understand how the GHS classifications actually dictate the physical control measures we put on the factory floor.
Exactly. Understanding GHS is not just about answering 5 multiple-choice questions in Domain 2. It is the absolute bedrock of managing a facility's safety program.
Right.
If you cannot identify the intrinsic hazards using the GHS criteria, if you don't truly understand the physical and chemical difference between a Category 1 flammable liquid and a Category 4 combustible liquid, you cannot effectively apply the hierarchy of hazard controls.
Give me a concrete, real-world example of that failure in synthesis. How does failing to understand GHS get someone hurt?
Let's say you have a new manufacturing process using a solvent. You glance at the SDS Section 2 and see the flame pictogram and the signal word danger.
Okay, fire is bad.
If you don't deeply understand that this means a very low flash point and high volatility, you might just specify a standard commercial electrical exhaust fan for ventilation.
Oh, I see where this is going.
But because it's a Category 1 or 2 flammable, the vapor can ignite at room temperature. You actually need an intrinsically safe, explosion-proof electrical system to prevent the fan's motor from sparking and igniting the vapor.
Your failure to deeply understand the GHS classification, to just see a picture of a flame and think fire is bad, just created a massive bomb on your factory floor.
That is incredibly sobering, isn't it? It proves that GHS isn't just bureaucratic paperwork. It is the architectural blueprint for physical safety engineering.
Exactly. You must integrate GHS data into your risk matrix methodologies for ranking and mitigating risks, which is another massive concept in Domain 2.
The entire severity axis of your risk matrix is directly informed by the GHS hazard category. You can't calculate risk if you don't understand the GHS baseline.
We have covered an immense journey today. Let's do a synthesized recap of the territory we just conquered.
Sounds good. Let's review.
We explored the historical, global chaos of chemical shipping that necessitated the UN's Purple Book in the aftermath of the 1992 Earth Summit.
We defined the exact scope of the standard and deeply explored the boundaries of the article's exemption.
We decoded the strict geometry, psychology, and logic of the visual label and its standardized pictograms, exploring concepts like warning fatigue.
We broke down the rigid, ergonomically designed 16-section architecture of the safety data sheet into logical clusters.
And finally, we tied it all directly to the core competencies required to earn the ASP credential and protect workers on the floor.
Mastering GHS makes you a vital part of a global safety network. When you walk onto a shop floor tomorrow and you correctly interpret a Section 8 exposure control limit, or you see a Category 1 flammable liquid pictogram and immediately check for proper grounding cables.
You are utilizing a harmonized system designed by thousands of experts over decades to protect millions of lives worldwide.
You are speaking the universal language of safety.
That is a powerful and empowering way to look at it. You aren't just reading a label, you are tapping into a global consensus of human protection.
It really is a global effort.
As we wrap up today's QHSE talks, I want to leave you, the listener, with a final concept to mull over. We talked about how the UN continues to update the science in the GHS, but think about the medium of communication itself.
Oh, the technology.
Right. How long will it be until safety data sheets are no longer static paper documents sitting in a dusty yellow binder on a warehouse wall?
Probably not long.
How long until they are dynamically updated, digital profiles integrated directly into smart PPE?
Imagine that. AR glasses.
Exactly. Imagine AR glasses that project the exact SDS hazard warnings and required PPC into a worker's field of vision the moment they approach chemical vat.
The intrinsic chemical hazard of the molecule will remain the same, but the technological communication of that hazard is on the verge of a massive revolution.
Exactly. As a future associate safety professional, you won't just be enforcing the current standard. You will be tasked with adapting to and managing the next evolution of hazard communication.
Best of luck to everyone studying.
Thank you for tuning in to this extensive session of QHSE Talks. Keep studying the blueprint, stay safe on the floor, and keep analyzing the hazards around you. We'll see you next time.